Today we will learn about dispersion forces. Our question of the day is, why is hydrogen bond a terrible name for an intermolecular force? In order to look at intermolecular forces, we first need to draw the Lewis structure for each element in their diatomic state. Then note whether they are polar or nonpolar. Finally, label any partial charges. Fluorine bonded to itself will be nonpolar. Chlorine bonded to itself will be nonpolar. Bromine bonded to itself will be nonpolar. And iodine bonded to itself will be nonpolar. Notice how all diatomics are nonpolar. Now let's look at some information about these. Well, fluorine has a total of 18 electrons and an atomic radius of 71 picometers, which is a really tiny measurement. Chlorine has a total number of 34 electrons, and its atomic radius is 99 picometers. Bromine has 70 electrons total and an atomic radius of 114 picometers, and iodine has a total of 106 electrons and an atomic radius of 133 picometers. Notice how when you go down a group, the atomic radius goes up. This means that their electronegativity, or ability to attract electrons, will go down because the electrons are shielded by the extra electron shells in the middle. Now, when molecules are nonpolar, they have their electrons equally distributed across the molecule because the molecule is symmetrical. You can think of the halogens, for instance. They have both nonpolar bonds and nonpolar molecules, so their bend and snap are both nonpolar. When we compare their sizes, we see that the radius of fluorine is much smaller than that of iodine because fluorine has only 2 shells of electrons, or 9 total electrons, and iodine has 5 shells of electrons, or 53 total. There are more electrons in iodine, and they will move around in a fluffy cloud of probability, or an electron cloud. When iodine collides with other atoms, these electrons get bumped into and warp the shape of the cloud. Cloud warping will create a temporary partial charge. These partial charges will attract and repel the partial charges on the other molecules. The result is an intermolecular force called dispersion forces. So, a dispersion force is the type of intermolecular force caused by the warping of electron clouds. They are the primary intermolecular force for nonpolar molecules. They result from a temporary and very instantaneous dipole. Because iodine has a lot of electrons, it takes a while for them to get back to where they belong. Fluorine's electrons are closer to the nucleus, and there are fewer of them, so they don't move as much. If they get banged into, they can quickly move back to where they belong. That means that the more electrons a molecule has, the more significant the temporary partial charge will be. So dispersion forces are stronger when there's more electrons. The halogens are often referenced as a perfect example of the effect of adding electrons to nonpolar molecules with nonpolar bonds. Since dispersion forces exist only because of temporary partial charges, they are considered the weakest of all intermolecular forces. So, as of right now, we know that hydrogen bonding is extra strong dipole-dipole, and dispersion forces are weaker than dipole-dipole forces. Now, pause the video and try the show what you know questions. Let's try applying what we know. Of the following nonpolar molecules, list in order of weakest to strongest dispersion force. Now, CH4 has a bunch of different atoms. It has 5. But notice how the atoms on the outside are all hydrogen. And hydrogen only has 2 electrons that are between it and carbon. So they're kind of protected, which means CH4 is going to be very weak dispersion force because there's not a lot of movement that can occur in the electron cloud. If we look at CO2, we have something similar. So we have two of our pairs between the carbon and the oxygen. So those atoms are kind of holding the electrons between them, which means the only part that can move is the part on the outside. That means that the dispersion force is going to be a little bit stronger than in CH4, but it won't be the strongest. And then for Br2, well, we have a lot of electrons on the outside, and they're not very close to the center compared to oxygen and hydrogen. So that means that Br2 is going to have the weakest. Now, if we look at C2H6, then we see that there are a bunch of hydrogens on the outside, and hydrogen has very few electrons, so it's going to have a very weak dispersion force. Now, for the other two molecules, we have Cl2 and CCl4. Well, while they both have Cl on the outside, which means each Cl has the same number of electrons, the one on the left has less chlorine than the one on the right. So it has less electrons on the outside that can be warped, which means Cl2 has a weaker dispersion force than CCl4. Now, let's look at number 3. We already know that hydrogen can only have 2 electrons, so its dispersion force is very weak. There's not many places those 2 electrons can go. They're kind of trapped between the hydrogens. However, oxygen, or O2, has 6 valence electrons, and 4 of these are going to be part of lone pairs. So these can move around a little bit more. Iodine, which has a large number of electrons and its valence shell is far away from the center of the atom, is going to move around a lot more. So it's going to have the strongest dispersion forces.